Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover trigonometry. This content was produced with AI assistance and reviewed by a human instructor. Trigonometry, pi, and e, a deep unity. So far, trigonometry has been geometry, the measurement of triangles, circles, and waves. The most surprising fact about the subject is that it is also, secretly, the mathematics of exponential growth. The functions sine and cosine, born from triangles and chords, turn out to be the real and imaginary parts of a single complex exponential. The bridge is a single formula due to Euler, and building it takes three pieces: arc length, sector area, and the meaning of pi. You have already seen that arc length on a circle of radius r is s equals r theta when theta is measured in radians. The full circumference 2 pi r corresponds to a full angle of 2 pi radians, so pi is exactly circumference divided by diameter. The fact that pi appears in trigonometry is therefore no coincidence with circles. It is the same pi in both places. Every formula in trigonometry that contains a pi is ultimately a statement about circles. Figure 32. A circle with a marked sector. The radius r runs from the center, an angle theta in radians opens between two radii, and the arc s equals r theta sweeps along the rim. The shaded pi slice sector has area A equals 1/2 r squared theta. The two formulas express the same angle on two scales, linearly along the rim, quadratically across the slice. Worked example, pizza slice. A pizza of radius 25 centimeters is cut into 8 equal slices. Find the arc length along the crust of one slice and the area of one slice. One full turn of 2 pi radians is divided into 8 equal parts, so each slice subtends an eighth of it. Theta equals 2 pi over 8, which simplifies to pi over 4 radians. Apply the arc length formula s equals r theta, with r equal to 25 centimeters and theta equal to pi over 4. S equals 25 times pi over 4, which is approximately 19.63 centimeters. Now apply the sector area formula A equals 1/2 r squared theta with the same radius and angle. A equals 1/2 times 25 squared times pi over 4, which is 625 pi over 8, approximately 245.4 square centimeters. One slice has a crust arc of about 19.63 centimeters and an area of about 245.4 square centimeters. Power series for sine and cosine. Sine and cosine, defined geometrically, also satisfy beautiful algebraic identities involving infinite series. In each series, x is in radians, and n factorial denotes the product n times n minus 1. All the way down to 2 times 1. Equation 32, the Madhava series for sine. The sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on, alternating signs on every odd power of x. Equation 33, the Madhava series for cosine. The cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on, alternating signs on every even power of x. Both series converge for every real number x, and they converge quickly when x is small. They are sometimes called the Madhava series, after the 14th century Indian mathematician Madhava of Sangamagrama, who discovered them more than 250 years before Newton, Gregory, and Leibniz rediscovered them in Europe. Animation 16. The true sine curve stays fixed in navy, and the Madhava series is added one term at a time in amber. A single term, y equals x, matches sine only near the origin, but 3 terms already hug the curve from negative pi to pi. By 7 terms, the polynomial tracks sine across nearly a full period before peeling away. Adding more terms widens the match without limit. Figure 33. Convergence of the Madhava series for sine over the interval from negative 2 pi to 2 pi, with the true sine curve drawn solid. The 1-term truncation is a straight line through the origin. The 3-term truncation follows sine from about negative pi to pi, and the 7-term truncation matches sine for nearly a full period before diverging at the edges. The exponential function has its own series, which you may have met before. Equation 34, the exponential series. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and on without end. Here e is the base of the natural exponential, approximately 2.718. Notice there is no sign alternation. Every term is added. Look carefully at the 3 series side by side. The one for e to the x contains all the terms. The series for cosine x contains only the even index terms, but with alternating signs. The series for sine x contains only the odd index terms, also with alternating signs. The 3 series are built from the same building blocks. The only question is what makes the signs alternate. Here is a question to sit with. If the series for sine x, cosine x, and e to the x are built from the same powers of x over the same factorials, what happens if you feed an imaginary number into the series for e to the x? Try to predict the answer before continuing on. Euler's formula, rotation as exponential. The answer to that question is Euler's formula, published in 1748 and one of the most consequential identities in all of mathematics. Equation 35, Euler's formula. E to the power I theta equals cosine theta plus I times sine theta. Here I is the imaginary unit, defined by I squared equals -1. To see why this holds, substitute x equals I theta into the exponential series and use the powers of I, which cycle through I squared equals -1, I cubed equals I to the 4th equals 1, and back again. Worked example, deriving Euler's formula from the exponential series. Substitute x equals I theta into the series for e to the x, then group the real and imaginary parts. Write out the first several terms of the exponential series with x replaced by I theta. E to the I theta equals 1 plus I theta plus the quantity I theta squared over 2 factorial plus the quantity I theta cubed over 3 factorial plus the quantity I theta to the 4th over 4 factorial, and so on. Simplify each power of I using the cycle. I squared equals -1, I cubed equals I to the 4th equals 1, which then repeats. This becomes 1 plus I theta minus theta squared over 2 factorial minus I times theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus I times theta to the 5th over 5 factorial, and so on. Separate the terms with no I, the real part, from the terms carrying an I, the imaginary part. This equals the real group. 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus and so on, plus I times the imaginary group, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus and so on. The real part is exactly the cosine series, and the imaginary part is exactly the sine series, confirming that e to the I theta equals cosine theta plus I sine theta. The conceptual meaning is the most beautiful part. Multiplying any complex number by e to the I theta rotates it by the angle theta in the complex plane. The exponential function, fed an imaginary number, becomes rotation. Rotation around the unit circle and exponential growth along a real line are the same operation, just viewed in different directions of the complex plane. Animation 17. A point e to the I theta starts at 1 on the real axis and begins rotating counterclockwise around the unit circle. Its shadow on the real axis is cosine theta, and its shadow on the imaginary axis is sine theta, both changing as the point sweeps. As theta runs from 0 to 2 pi, the point traces the circle exactly once. Feeding an imaginary exponent produces pure rotation. Figure 34. The unit circle in the complex plane, with the real axis horizontal and the imaginary axis vertical. A point e to the I theta sits on the circle of radius 1 at angle theta. Its real part is cosine theta, and its imaginary part is sine theta. Here is a reflection. Multiply two complex exponentials. E to the I alpha times e to the I beta equals e to the I times the quantity alpha plus beta. Apply Euler's formula to expand both sides into sine and cosine. What does this reveal about why the sum and difference identities from the identities section have the form they do? Euler's identity, the most famous equation. Now set theta equal to pi in Euler's formula. The right side becomes cosine pi plus I sine pi, and since cosine pi equals -1 and sine pi equals 0, it collapses to -1. The left side is e to the I pi, so e to the I pi equals -1, or moving the -1 across, the famous form. Equation 36, Euler's identity, e to the power I pi plus 1 equals 0. The physicist Richard Feynman called it our joule, and the most remarkable formula in mathematics. Look at what this one line contains. 0, the additive identity. 1, the multiplicative identity. I, the foundation of complex numbers. Pi, the soul of geometry. And E, the base of natural growth. 5 fundamental constants, linked by addition, multiplication, exponentiation, and equality in a single 9-symbol equation. There is no slack in it. Every symbol is essential. Here's a reflection to close. The 5 constants in Euler's identity each entered mathematics for a different reason. 0 and 1 from arithmetic, pi from circles, E from exponential growth, and I from solving polynomial equations. They were studied for centuries before anyone saw they were related. What does it mean that an equation written in 1748 still feels meaningful to physicists and mathematicians today? That wraps up trigonometry P and E, a deep unity. Next up, Section 10, Trigonometry in the World. If you found this helpful, like and subscribe and support the channel.